The next exercise is an odd numbered one, number 15, but we are going to need this. So let's see what it's saying. Here we have a non-zero ring A, in which we are considering X, which is the set of all prime ideals. From a previous result, you know that because A is non-zero, it has at least one maximal ideal, which is of course also prime. So that means X is non-empty. So there is at least one prime ideal. Now for any subset E of A, we consider V of E, which is the set of all prime ideals containing E. That means the elements in V of E are those prime ideals, that means elements from X, which contain E inside of them as a subset. Then we have to prove the following. There are 4 parts. Today we are going to prove the first 2. This is part 1. If I is the ideal generated by E, then V of E equals V of I, which equals V of the radical of I. So let's first solve this part itself. We start the solution like this. Since E is a subset of I, so V of I is a subset of V of E. How? This is how. I is the ideal generated by E. So by definition, I is the intersection of all ideals of A which contain E inside of them. So if all of them have E as a subset inside of them, then their intersection would also contain E inside of it, which is I. So that's how E is a subset of I. And now if you take any element P in Vi, what does it mean? It means that T is then a prime ideal which contains I inside of it. But because E is already inside I, so P would then contain E also. So then P becomes a prime ideal which contains E inside of it. And so by definition P would then belong to V of E. So that is how any element P in Vi is also in VE. So that's how you have this containment. Now we will show that the reverse containment is also true. So that's how we will get the first equality. For the reverse containment, we let P be any element in VE. So this time we want to prove that any element here is also there. So what does it mean? It means that then P is a prime ideal containing E. And then again, just like this explanation, this time we have actually written this in the solution itself, that what I is. Since I is the intersection of all ideals containing E, so P would also contain I. Why? Because P is a prime ideal containing E. That means P is after all also an ideal which contains E inside of it. So the intersection that you consider, which is I, in that intersection you are considering those ideals which are containing E inside of them. And P is one such set in that intersection. So obviously the intersection would be a subset of P. But then what does that make P? It makes then P an ideal, and not just that, a prime ideal which contains I inside of it. So by definition of Vi, P belongs to Vi. So that's how any element here is also here. So that means VE is also a subset of Vi, just like Vi is a subset of VE. So that's how they are equal. Next, we recall this containment that we already know. Any ideal is contained in its radical, and because of that, V of the radical is contained in V of I. Now this one needs no explanation. You already know how. You go to the beginning of the solution and there you see how. Now here also we want the reverse containment, for which we take any element here and say that is Q. What does it mean? It means that Q is a prime ideal of our ring which contains I inside of it. Alright, although we did not write that Q is prime, but it's understood. Right now, however, we only focus on this part. Now next what we do, we take any element A in the radical of I. And you recall the definition of radical. This just means that some positive integral power of A then belongs to I, where the exponent n is some positive integer. Okay. But then because I is the subset of Q, A to the power n will belong to Q as well. And now you use the fact that Q is the prime ideal. So because A to the power n belongs to Q, primality implies that A has to belong to Q. Note one more thing, that n is a positive integer. If you don't immediately see how primality implies this, you argue like this. This n may not be 2 actually. N may be more than 2. If n is 1, there is nothing else to do. You automatically have A in Q. If n is 2, then you have A squared in Q. But because Q is prime, either A is in Q or A is in Q. So that means you are having A in Q. But say n is 3. Then you write A to the power n as A squared times A. Then primality tells you that either A is in Q or A squared is in Q. If A is in Q, fine. Otherwise A squared is in Q, and then you can continue the argument. No matter what n is, you eventually get this. Alright, but then what are we getting? From this part to this part, that any element in the radical is also in Q. So the radical is a subset of Q. But then Q becomes a prime ideal containing R of I, which just means that Q belongs to V of R of I. So that's how any Q in Vi is also inside VRI. So that's how Vi is also a subset of VRI, and that's how we have equality. So this is the second equality. Part 1 has been solved. Part 2 is pretty simple. V of 0 is X, where 0 is the 0 ideal and V of 1 is the empty set, where this 1 is actually not just the identity element 1, but it's rather the ideal that it generates. That means the entire ring. And the solution is also pretty easy, since every prime ideal of A contains the 0 ideal 0 inside of it. So X is a subset of V of 0. It's just a simple thing. But of course, we also have this containment already, because no matter what set E you have here, in this case you have 0, but no matter what E you have, what is V of E? V of E is the collection of all prime ideals which contain E. So automatically V of E is a subset of X. So this is also a subset of X. So that's how you have the first one. And the second one is also as easy to obtain, since every prime ideal is by definition a proper ideal of the ring. So none of them contains the entire ring inside of it. And that is why V of the entire ring remains empty. No such ideal is there which contains it and which is also prime. And the video ends here. By the time we will solve the other two parts also in the next video, you will realize that here we are looking at a topology on the set X of all prime ideals. So in this topological space, the prime ideals will be points. And in this space, these VEs, these sets will be closed sets. It has a name also, it's called the Zariski topology.